Hello everyone, welcome back to Physics by the River. Today I'm joined by Professor Charles Adams. How are you doing today?
I'm good, actually. It's been a busy day, but I'm enjoying it.
Nice. Wow. What better way to de-stress than answer some physics
Yeah,
questions?
I'm
Yeah.
nervous. I mean, I've never done this before, so let's see. I'm also looking forward to it as well.
Hopefully you'll find it fun. So to start, I wanted to ask how your path into academia began.
Well, that's kind of a long story, but I guess I realized at school that I liked physics and I was good at physics. So then went on to university and did physics. And I wasn't necessarily thinking of doing research initially. I was thinking maybe going into more industrial research. And at university, I went to a seminar on lasers, and that inspired me. I wanted to work on lasers at that time. And then I also wanted to go abroad. So I was looking for some opportunity where I could sort of go overseas and work on lasers. And then the academic route was the best way of doing that. So I looked at going to either Canada or Australia, and I applied to some universities to do masters and PhDs, and I got offered a place in McMaster University in Canada to do a master's by research on lasers. So I did that, and I was still thinking I would probably go into industry in some form, but. So I started doing this master's, and then we got some results, and I submitted. Submitted a paper to a conference that was in California, and I went and delivered my conference talk. It was only 15 minutes, but it was massive. I mean, there was about 400 people in the room. And it's still one of the biggest conference talks, my first conference talk, and one of the biggest audiences I've ever had to talk to. And people came up and asked me questions afterwards. I felt it had gone disastrously, but it seemed to have gone quite well. And I just was so fired up about that the whole process of doing science, communicating science, and then the fact that people seemed to care, and all these people turned up and wanted to hear what you had to say. So it was at that stage I decided to do a PhD, again in laser physics. And then I did a PhD in laser physics at Strathclyde in Glasgow. It also went very well. We built this laser that became quite a successful commercial product afterwards. But I got slightly frustrated with just building lasers, even though it was a new type of laser, because it was all about just can you get more power out of the laser. So, your supervisor comes in every day saying, how many watts have you got from your laser? What's the performance? And I went to some conferences and meetings where people were using lasers more than building them. And that was more about quantum physics. And I thought, well, I really want to work on quantum stuff, using lasers to do quantum things. So when it came to looking for postdocs, after I'd got my PhD, I looked at groups where I could use lasers for things like laser cooling, which was a big thing at the time, looking at using lasers to cool down atoms. So I did 2 postdocs in the area of light manipulation or laser manipulation of atoms, first in Germany and then one in the US. And I did laser cooling in the US. At Stanford, and then I got the job here and then set up a laser cooling group, and then we did lots of experiments with cold atoms. We also did some lasers interacting with hot atoms, and we've been pushing more and more in the direction of doing quantum-y things, generating single photons, aiming towards quantum entanglement, quantum optics. So it's just evolved in that direction. But so really using light and atoms to do interesting quantum stuff, because I became just fascinated by the quantum question and the things that we don't yet understand, and trying to make simple experiments that help us to answer these fundamental questions, if there are answers.
Okay, that's quite a tale.
Yeah. It's a long journey, but I've been, it's a long story. I've done over probably 3 decades now of research. So
Got a lot under your belt.
yeah.
I'm quite interested that you said you're like keen to go abroad.
Yeah.
Were there like any particular reasons why you wanted to do work?
Well, there was some. I think that when I grew up, so I come from the northwest, a town called Rochdale that people might know. It's on the outskirts of Manchester, but it's not. It's not a great place to live. So when I was at school, I mean, with my friends, our main aim was to get out of Rochdale. So we had to study hard, do well at school, and then we could get out. And so I got out and go to university. But then somehow that wasn't enough. So the next step was to get out of Britain. So I was desperate to leave. But not because I hated Britain or something. It was just that I was searching for more adventure. So once I'd moved, one step was to move out of your hometown to a more interesting town. And the next step was really to move out of the country. So it was just something I wanted to experience. I was fascinated by other countries. So I really wanted to sort of go abroad and have that experience of living in another country, living and working in another country. And it has been I would say one of the most wonderful things about the career of being an academic has been that opportunity, if you want it, to work in different places. I mean, there's only a finite set of countries maybe that you can go and work in. Maybe not, but I mean, there's some countries have more to offer to academic physicists than others. But I have had the opportunity of living and working in Canada, Germany, US, and I've spent quite a lot of time in France as well. So, which is, that's a real plus.
Yeah, it does sound really interesting. I've been thinking a bit about maybe doing something like abroad after my undergrad. I think that'd be really interesting. But we'll see.
Yeah, I think it's definitely something nice if you have that opportunity. A nice thing to explore, and you learn a lot about because Britain's only a small place, right? But we sometimes tend to think it's everything, but it's a very small part of the world.
So you've done physics in quite a lot of different places, and what would you say what if any were there big differences?
Yeah, there's different approaches in different countries. I think that we're very creative in Britain, so I think that's a strength here. Sometimes maybe we're not quite as there's the idea of the sort of the gifted amateur or something. So sometimes we're maybe not as and sometimes the funding is not quite as good here as some other countries. So if you go to Germany, I think that they have more funding. US has more funding, but only if you're in a sort of top group. They work very, very long hours in the US. They don't take many holidays, but then they're not necessarily as efficient on a day-to-day basis. Whereas in Germany, they're very, very efficient. Sometimes they won't talk to you in the corridor, but then they take their holidays and they'll go home in the evening. So there are sort of cultural differences. But also our science is very international. So in general, you'll find, I think the best teams always have people from many, many countries anyway. And you tend to find that when you join a group that there'll be people from all over the world. And if anything, it's become even more international. Hopefully that carries on. I mean, it's getting a bit more difficult now to move to some countries, but and also for people to come from some countries. But I think it's always been a strength of the scientific community, just in how international it is.
Yeah, I think the kind of prospect of being able to meet such a varied kind of range of people also interested in physics is a big, I guess, something that appeals to me for like going into academia.
Yeah, it's like a global community, and you feel part of something, and you feel sort of welcome in that group. And
it's quite nice.
and hopefully everyone's pulling together in the same direction, because we all want to advance science, so everyone's got a similar goal.
Nice. I think I'm gonna go address the can of worms that is quantum optics. Could you explain a bit about how that, like, what that is and how it differs from just kind of standard optics?
Yeah, so the whole thing about quantum is, so quanta means counting, really. So we know that light is made of photons, and we can count photons. So really, quantum optics is about the control and the application of light on the single or few photon level. So when you're really exploiting those photon properties. So you want to have ways of producing single photons or two photons, ways of measuring them, and ways of looking at correlations or entanglement between photons. So people are now working with, quite a few photons. So you might work with, say, 16 photons that are all entangled with one another. But that's about the sort of scale of things, I guess. And most people are working either with one or two photons in the quantum optics area. So few photons. So it's white light at its very, very weakest level. But what's interesting about that is the photon is a fundamental particle in the particle physics sense, and it's also very accessible because we don't have to go to CERN or somewhere to get this part. These particles are all around us, but actually looking at things at the single photon level is quite tricky, because obviously there are loads of other photons in this room at the moment. There's more than trillions, trillions and trillions of photons kicking around. So if you want to work with a single photon, you have to make it completely dark, and you have to have a particular type of detector called a single photon counter. And then you have to control the light in order to... And that's something that's only really happened... it began in the 70s, I guess. So it's about a 50-year-old field experimentally, but the idea of photons is much older, but people really doing experiments with them has only sort of come about in the last 50 years, and now there's a lot of progress, and there's also quite a lot of applications of quantum optics in different areas. Things like, you can use photons for quantum computing, you can use photons for communication, so there's like quantum communications. You can have a secure communications using individual photons. So things like that. So there's both a fundamental side and an applied side to it.
Do you have any kind of specific hopes for the research you're doing in terms of practical applications?
Well, that goes in different directions, not just the sort of quantum direction. So I'd say for me the quantum question is more fundamental and more of a science question of trying to understand what entanglement really means, and whether we can get any new insight into that with the type of experiments that we might be able to do. So one of the things we worked on for the last decade or so is whether we can make photons interact. So normally photons don't interact, so they just pass through one another. So if you send two beams of light, they'll just cross, and there are no photon-photon collisions, at least at normal energy scales. But we were looking at ways that, can I make photons interact? And that's by giving them some character of say, matter. So when a photon travels through a medium, it actually picks up some of the character of that medium. And if we can create an unusual medium where what's mapped onto the photon is something that can exert a force on another photon that has that similar character, then you can see photon-photon interactions. So that's what we tried to do over the last 10 years. And then if you can do that, you could say, okay, now I have interacting photons. What can I do with interacting photons? Well, if you want to do something like build a quantum computer out of photons, then you would really like to have photons that interact, because to make a gate, so if I want something like this photon switches that photon between channel 0 and channel 1, which would be a controlled gate, so this conditional on this photon being here, I can switch the state of this other photon, then you need an interaction between the photons. And so it was a kind of holy grail in the whole optics area, or quantum optics area, to make strongly interacting photons. And we did that, and the way we did it was by making our photons acquire a bit of character from what are known as Rydberg atoms. So Rydberg atoms are these atoms where the electron is very, very far from the nucleus. So the electron's very far away, so you have this giant atom, and these giant atoms can basically interact very strongly with other giant atoms. So if a photon goes in, creates a giant atom, and another photon goes in and creates another giant atom, then they interact very strongly, and that's the way that we make strongly interacting photons. Now, and we can do all that now, which is brilliant, but whether you can, we haven't really found out how to make it into a sort of practical, useful device. So it works at a fundamental level, but it doesn't work well enough to be really useful at the moment. But maybe in the future we'll find a way of making it work in a more practical way. If you like, it works, but not very efficiently. And if we wanted to use it for quantum computing, we'd need it to work with sort of 99.99% efficiency or something like that, which is quite hard to do.
So is that like to do with quantum entanglement, or is that...
Yeah, so entanglement is the interaction. So to get in quantum entanglement, you need things to interact. So I can't entangle two particles, whether they're photons or any type of particle. I cannot entangle them unless they interact with one another. So entangling photons is if I have two photons that are not entangled, to make them entangled is a tricky thing. The only way to create entanglement, quantum entanglement, currently using photons, it's what's called post-selection. So you select certain events from all the events that do happen, but they're improbable. So when you try to repeat that process many times, the probability goes down and down and down. It's like trying to throw 8 sixes in a row or whatever. It just doesn't happen very, very often. So what you would like to do is have a way of deterministically creating entanglement, but that means that you've got to make the photons interact with one another. So that's been a big holy grail for the whole optics or quantum optics community, of how to make strongly interacting photons. And we found one way of doing that using these Rydberg atoms.
Yeah, when you mention those like Rydberg atoms with electrons far away, I envision like a nucleus like wrapped up in 100 like layers of coats and jumpers.
Yeah, it's a bit. It's sort of really like blowing the atom up, so it's like a massive expansion. And these, if you compare, sometimes people make these scale comparisons that if a normal atom is like a tennis ball, then one of these Rydberg atoms would be have a dimension that's bigger than this tallest building in the world.
Oh, wow, okay.
So the scale differences are really, really quite enormous.
These Rydberg atoms need to go on a diet.
Yeah.
So are there any like particular reasons why we don't have a good kind of definite way to entangle photons together? Like, why do we need to rely on probabilistic methods?
Well, because they don't interact. So because photons fundamentally have no interaction. So there are no forces on a photon. It's a non-interacting particle, which is very different to an electron. So an electron has a Coulomb interaction with another electron, but a photon doesn't have any interaction with another photon.
Okay.
And that makes control. In a way, that's good, because if they did all interact with one another, then seeing things would be a problem. Because rather than photons traveling in straight lines from A to B, and then we see what things look like, all the photons would be interacting between A and B, and they would all get in a terrible mix-up. So it's good. So it's good that photons don't interact. So that's a plus point. But then it's also a downside in that it means that some aspects of we find difficult to control. It also means that because photons don't interact, it means that they're very useful for communication and sending from A to B. So the optical fiber communications, for example, are very, very powerful because I can send a photon round the world and it comes back and it's exactly the same photon that I sent, and it does it very fast.
Quite reliable.
Yeah, they're reliable. They are very reliable. Yeah.
So, I think earlier towards the start, you mentioned something about the quantum question.
Yeah.
What do you mean by that?
Yeah, so there's an aspect of quantum physics that we just can't get our head round, and it kind of comes back to wave-particle duality, which is also the essence of quantum optics, because for photons we understand that light is a wave, but it's also this particle. And we really struggle with this issue of how it can be both wave and particle. The famous French physicist Alain Aspect puts it nicely that if I ask light the wave question, are you a wave? It says yes, I'm a wave. If I ask it the particle question, are you a particle? It says yes, I'm a particle. But it can never be both at the same time. So our human mindset is always set on something has to be one or the other. It has to be wave or particle, but how can it be both? But the experiments definitely show that it has both of these aspects. So it both displays interference, which is this particle-like property, which is the wave-like property, and you can count the photons, which is the particle-like property. So when you mix those two things together, you get answers that just don't fit with our human intuition in any way. So, and you kind of have to resort to mathematics to describe this, but you can't help feeling that there should be some way of understanding it that's a bit more intuitive rather than just resorting to writing down some strange equations that seem to describe everything. So we're kind of hoping that these simple experiments on a few photon systems give us pictures or more insight in a way that we get a more complete picture of what's going on at the quantum level.
So do you think we'll ever get a satisfactory answer? Because
that's an interesting question and a hard question, because I mean, there's a lecture that I like from Feynman. He gave these messenger lectures at Yale University, I think in the 60s, and there's lots of famous quotes from Feynman at those lectures, and he says nobody understands. He says there might be 10 people in the world that really understand general relativity, but as for quantum mechanics, nobody understands quantum mechanics. And and he was one of the pioneers and won the Nobel Prize. And then you sort of think, well, if Feynman didn't understand quantum mechanics, what hope for the rest of us? And he also says, don't keep asking yourself this question, how can it be like that? How can the quantum world be so bizarre? His argument is just sort of accept it and then just use that and make predictions, and they will come true because the theory is good. But I always feel that I do want to ask that question, how can it be like that? And I think asking the right questions and looking for more insight is sometimes the way to make new discoveries, and not accepting that people say, oh, well, that's not going to work, or we're never going to understand that. I think if you start to just accept what people have said, and you don't decide, well, I'm interested in this question, so I'm going to go and try and answer it, even if you don't know how to answer it, just being interested in the question is enough motivation to make you a scientist. And you may find that you're spending a lot of time not really answering that question, but you actually started down this road because you wanted to answer that question. And even if you never get to that answer, at least you've done something worthwhile, hopefully.
Yeah, it's quite funny how, I'm sure for a lot of people, the motivation for going to science is like curiosity.
Yeah, I
and
think
wanting
that's
to
exactly it.
explain things.
Yeah, I mean,
But
first
then-
you want to understand. Yeah, so and if you find something you don't understand, then that's the place to look to be more curious, I guess.
Yeah, but then with quantum mechanics and stuff like that, it's like the most kind of bizarre
Yeah.
thing, and then people kind of go the other way, like, wow, it just is what it is, you know.
Yeah, I think that, I mean, there's different things you have to do, because if you're just doing your undergraduate exams, then you just need to sort of get familiar with the techniques and the equations, and so that you can answer the. But hopefully that doesn't completely destroy the thing that made us all physicists in the first place, which was this curiosity of trying to answer these bigger questions like origin of the universe. Why is it quantum? And so that's the thing that we want to sort of keep alive, even in our teaching a little bit, to ask those, to keep that curiosity and say there's still things that we could understand better, still questions to answer.
It's like doing first year, I'm like struggling trying to sketch like a wave equation, and then but I still feel like I barely get what a wave equation is.
Yeah, I think that's true. I mean, we often don't spend a lot of time discussing those. I mean, it's almost in the realm of metaphysics, So you've got an equation, you've got this psi, and that's your wave function, and then we know there's measurement, and people talk about collapse, and and there are all these words, but what's really going on? Have I really understood what's going on? And when you go and ask me or some other quantum person in the department, do they really understand what's going on? Probably not.
Well, Feynman didn't.
Yeah, Feynman said nobody understands it. So I always think, well, I'm in good company. If Feynman didn't, I'm in good company, and he didn't give up though. So
fought till the end.
Yeah. Well, Feynman, interestingly, pretty much came up with the whole quantum computing. So he asked the question, what happens if we start to build computers out of individual atoms or individual particles? And that was in the 80s. It was one of the final sort of pieces of work that Feynman did. And when you read some of his articles, it's interesting because he almost admits, this is a crazy question, because like back in the 80s, nobody thought it was technologically feasible to make computers out of single atoms. And he writes in one of his articles, he says, let's imagine making a computer out of single atoms, because that's the crazy kind of thought that a professor like me likes to have. But I mean, that started a whole field, which now is massive, actually, and everybody now is talking about, and there are companies and making these things, Google is investing billions, and it all starts because somebody's curious enough to ask the right question.
Yeah. Quantum computers are quite exciting, although I'm like dreading the thought of having to troubleshoot a quantum printer.
Well, yeah, when the paper comes out, what you print out is in a superposition.
Oh, God. I'm like turning out into a sweat just thinking about that.
Yeah.
Is there like anything else you want to mention?
Well, there was one thing I was just thinking when you were talking about the quantum printer, because one of my colleagues, he often says, if you can see it, it's not quantum, which is also I mean, it is a nice summary, because once we can see it, or once any classical measuring device sees it, then whatever this superposition was, this quantum thing of it being two things at once, is no longer there. It can only, in the classical world, it can only be that or that, not both at the same time. So if we had a quantum printer, somehow, as soon as the printout is done, it wouldn't be quantum anymore. We would see it, and it's out there in the classical world, and now it's not quantum anymore.
Well, that eases my woes.
It eases your anxiety, does it? Yeah.
I'll be able to rest easy at night now.
Yeah.
having to dread the...
I don't know what the application would be. It's an interest. I've never heard of the quantum. There you go. You can invent the quantum printer and tell us how it's all.
I'd rather not. Printers are like the bane of my being.
Yeah.
I feel like I'd be betraying what I stand for making a quantum printer.
Yeah. Okay, yeah.
Thank you for coming on the podcast.
Well, it's been fun. Yeah. Really enjoyed it. Thanks a lot.
I'll see you all next time. Goodbye.